Hello team! Welcome to this video guide for programming assignment 4t, the semantic test checkpoint or preliminary exercise. And in this one you are asked to construct a rich test suite that features programs with correct syntax, that is, that pass programming assignment 3, but incorrect semantics, type errors. And this is sort of a different assignment than we've been faced with before. And we're going to use an insight from computer science theory to try to get an extra handle on it. And the notion is that we can really treat programs as data. And you now have the power, between things you've been doing for programming assignments 1, 2, and 3, to do that in an automatic manner, to really lift a lot of the manual burden that might be associated with this. We're going to do this two ways. You'll probably want to create some of your test cases by thinking very hard, maybe trying to make a particular error occur, and we're going to use the cool reference executable to get a list of possible error messages. But we may also want to create some buggy programs automatically, and for many of you this may be a relatively radical in the traditional sense idea. Can I write programs that write programs? Yes, we're going to do it, and it's not even going to take that long. We're going to try to flush out candidate bugs by swapping identifiers and types to make bad programs. We'll see that in a bit. And as usual, there will be some live submission demos. Those always work. All right, so let's get started over here. And just to get started, I have the cool reference compiler, cool.exe, and also the hairy scary example that comes with the cool example zip file that you've had for some time. This is this mysterious program that nobody understands, but it seems to have a lot of stuff going on. Initializers, case statements, a bunch of classes, addition, objects, blah, blah, blah. Looks good, right? And now we want to take a look at what we're supposed to be doing for programming assignment 4t, creating tests. And I'm assuming that you've read this text about test-driven development, but it's worth noting that this hint here at the bottom, because you can find positive bugs in your type checker more easily running your type checker on correct cool programs. The exercise is strongly biased towards negative bugs. That is, the secret buggy type checkers usually fail to report certain semantic errors. And the first thing we're going to do is just verify that. We're asked to submit a bunch of cool test cases. Well, maybe how I want to start is just hope that this one that we have lying around is going to be good enough. Right? So this is just harryscary.zip, and we'll put hs.cl in it. And let's go try to submit this. And here's our just harryscary file. Let's actually reload this just in case it needs to re-get my NetBadge authentication. All right, so we are doing PA4t semantic testing, and let's submit just harryscary and see what happens. And you can see that it's got our test case, harryscary.cl, but nothing seems to be happening. We did not reveal any of the 20 held out defects, and we need to get 15 of them for full credit. And indeed, while you can pass a few of them by just throwing, sort of cool examples back at the submission server, in general, the assignment is constructed so that you need to do a little more than that. Well, so we want to make programs that parse, but that are going to fail type checking. And one approach to that would be to look at the program and think very hard and say, what could I do to mess something up? Like, could I go in here and, change this to be doing something else, or like to return an integer instead of new bar? For example, as something simple, maybe instead of d returns object, since this is in class bar, we can see if the program still works when d is supposed to be a bar. No. Error, type check, int does not conform to bar in initialized attribute. Yeah, that was an initialized attribute, and we just changed the program to make it bad. Right? So that's something we could keep around and submit to the server. By contrast, something like this, let's say I put in random extra arrow sign, right? That's not good because this is a parser syntax error, and for this assignment, we have to submit syntactically correct programs that have type checking or semantic errors in them. So this double arrow isn't going to work. So, I guessed that if I put bar there, something bad happened, but there are other values where nothing bad happens, and the program runs doing whatever it's supposed to be doing. Let's not look too closely. So how do we know what to change? And this is where we want to get back to the first sort of insight we're going to use this notion of programs as data. And I want to direct your attention, if you haven't had the chance to take an undergraduate theory class, to the notion of a universal Turing machine. And that is when we say that something is Turing complete, or this notion that Turing machines could carry out any computation that another sort of model or another Turing machine could carry out. And this is that notion. The universal Turing machine essentially achieves this by reading both the description of the machine to be simulated as well as the input from its own tape. Let me just focus in on this. Achieves this by reading the description of the machine to be simulated. In Turing machine world, this means the source code. Right? This is like it reads in the source code to your program as well as the input, and the tape is as data. So one of the key insights in the universal Turing machine is that you can read in a program as data. Now the universal Turing machine is just going to simulate it. It's going to run your program. It's like an interpreter. But you don't have to just simulate it. You could mess it up. You could mix it up a bit. All right? So one of the ways that we can do that is to take advantage of some of the programs I've already given you. All right? One of the things we have access to is the cool reference interpreter. Let's just get that error message back once again. We saw that if we change this to bar, and we saw this error message, int does not conform to bar an initialized attribute. Now that's one error message, but the programming assignment description, it says the secret buggy type checker usually fails to report certain semantic errors. That's only one error. We probably need to find a few more in order to get all 15 of these held out bugs. So how do we know what they are? Now, the best way to do this, officially, is to read the cool reference manual, right? Take a look at the typing rules, go through all of the formality, think about how the program is supposed to work. Don't add integers to strings, that sort of thing. But I'm going to show you a different way to do it. In order for us to get this error message, int does not conform to bar, does not conform, fancy word meaning the types don't match up, right? Fancy words. Cool.exe had to print it out, which means that string does not conform. This has to be in cool.exe somewhere. Cool.exe is pretty big, 2 megs, right? But it has to actually be in there somewhere. Let's go see if we can find it. Does not conform. You can pull up binary programs in most decent text editors. And here we see does not conform to %s is like some string we're going to fill in, to %s in assignment, wrong number of actual arguments, argument does not conform. This is kind of hard to read though because it's this binary. Are we even allowed to do this? Yes, you can't hack my server, but the reference compiler is totally available to you. You can spend your time studying it if you so desire. But this, all of these weird binary characters, they make it hard to figure out what's going on. If only there were some way to just get like A through Z, A through Z, A through Z, A through Z star, something like that. Just get the words out of this, right? Wow, we could totally do this with regular expressions. Indeed, you could imagine writing a PA2 style lexer that just pulls out the sort of real English words plus some punctuation and leaves all of the binary junk that we don't care about behind. You could imagine writing that. Imagine it in your mind. You could totally do this. Or you could use the one that comes with Unix that someone has already written for you. It turns out there's a program called Strings, that's a standard on Unix and Cygwin, that looks for printable strings, say of length 4 or 5 in a file. For example, I could run strings on cool.exe and redirect the output to cool.txt. And now we will see that it has taken a bunch of things that look kind of like words, right? But if we keep scrolling down, does not conform, we can see that all of the previous error messages we were struggling to read are now separated out from all of that binary code. Does not conform in assignment, does not conform in static dispatch, argument does not conform. So one of the things I might do for PA4t is just scroll around and see all of the possible things that could go wrong in a cool program, binding self in a case expression, blah, blah, blah. Find all of those, and for each one, make a cool program that does that bad thing. Right? Think hard about it, use my brain, but basically, read each of these messages. Case branch type is bound twice, and try to make a program that does that. because if, as promised, the secret buggy type checkers are failing to report certain semantic errors, which they're doing most of the time, then if you can trigger all of these semantic errors and the buggy version fails to print them out, then you're revealing the bug. All right? So this is my hint for part 1. We can view programs as data. Indeed, you can view the cool reference executable as data to get out its error messages, right? Because it's not encrypted, because it's not doing anything tricky. They're stored in it as raw strings, right? And that's a resource you have access to if only you know how to read them. But let's take another approach to this, right? Maybe we won't be able to get everything rapidly by reading through all of these error messages. We saw earlier that we could reveal at least one error message by changing what was here. Like this was supposed to be object and we had changed it to bar. And I could do that other places. I could change this to raz, and I could change this to bar, and I could change this F to an E. I could sort of swap around all of the words in a cool program, and that would likely produce a program that still parses, but that fails type checking. Right? If I swap an identifier with an identifier or a type with a type. But there are a lot of types and identifiers here. That could take me a long time to do manually. I don't like to do things manually. Why don't we write a program to do it? And again, that's this notion of the universal Turing machine. Reads in the description of the machine, the source code, but we don't have to simulate it. We could mix it up. Let's write a Python program that takes in a cool program and mixes it up by injecting faults, by swapping words. W6Y, read in a cool program and mix it up or inject faults by swapping. Now there are a bunch of things we could do to inject faults. Like we could, if you have some expression like x, we could replace it with x plus 1. And then if x wasn't an integer, that would reveal something. I'm just going to show you one way to systematically change programs. There are many others. We will swap around identifier names and type names. There are many other ways to inject faults. All right. So we want to read in a cool program like Harry Scary, but in order to find the things that are actually identifiers, like we want to change foo, but we don't want to change class, because if we change class, it won't even parse. It won't make it through PA3. All right, so how are we going to do this? Well, why don't we actually make it relatively easy on ourselves? You don't have to redo work. Everything we've previously done in PA2 or PA3 is fair game. For example, if I just look at the tokens for harryscary.clx, every identifier is really obvious and is followed on the next line by what the identifier is. Similarly, every type is really obvious and is followed on the next line by what the type is. So why don't we read in a PA2 CLX file, read it in as a bunch of lines, right? We'll find all of the lines, type or identifier, put them in a big bag, draw two things out of the bag, swap those two things, and print out the result. And what we'll end up with is a new CLX file that has some of the words swapped around. Right? Now, one of the first things that's worth noting, the assignment asks us to submit cool programs, CL files. And if I follow through with this plan, I will end up with new CLX files. But it turns out that you could reconstruct a cool program from a CLX file. You just lose all the comments and all the spacing. And indeed, the reference compiler already has an unlexer and an unparser built in that do just that. You can unlex a CLX file, and it will produce a CL2 file, which is really just a cool file, that's the same as before, but with no white space and no comments. So it just uses the line directives that we store around to tell when to print a token and when to print a new line. So this is very similar to the original. Everything is on the same line. We've just lost all the white space and all the comments. See, ARAS is here, ARAS is there, but we've lost all this tabbing. Right? So we could unlex automatically. So if I can make a list of tokens and then mutate it, inject faults into it, mix it up, then I could automatically get some cool programs out on the other side and maybe send those back to the grading server and see how they work. Right? So just to re-verify, when I run this, it type checks, great. So now what I want to do is read in some file given to me on the command line. We'll open sysarg1, let's import sys in all of our Python files, open it for reading, and if memory serves, you can turn a file into a tuple in order to convert it into an array of lines. And just because we want to be cross-platform compatible, we will strip off all the white space. Right? And just to make sure that's working, we'll print it out. So can I run Python inject py on this? Right? And this looks pretty good. We've got a big list of all of the tokens in a row. So now what I want to do is find all of the, I don't want to say line numbers, find all of the positions that correspond to type or identifier. So we'll just go over the lines one by one. The current line is lines I, and if that line is in type or identifier, then I want to keep track of it. So like interesting positions. And conceptually, we just put, do something like this, add this to the list. Although, we'll just take a look here. You notice that if type occurs on sort of position 4, it's actually position 5, the one with foo, or the one with baz. That's the part we want to store. We don't want to change this file by replacing type with type from somewhere else. That wouldn't actually change it. We need to change the things that occur on the next line. Okay. So we'll do something like I plus 1. All right. And to see if this works, we will print out all of the interesting positions. All right, so it looks like some interesting positions are 4, 9, and 14. Let's just go see if that matches what we expect. Here's 4, let's get rid of that. Here's 4, which is type. Here's 9, which is type. Here's 14, which is identifier. And it looks like we are still off by 1. Oh, we're off by 1 because Python is counting from 0 and my editor counts from 1. We're not off by 1. We're totally fine. All right. So now what I want to do is produce a number of new CLX files, each of which has one interesting position swapped. Now you could do a bunch of different things. You could add in plus tokens, you could swap multiple things. There are a bunch of different ways you could poke a file automatically. I'm just going to show one way. Indeed, why don't we produce like, I don't know, 80 new CLX files. So we'll have J in range 80. And what we want to do for each one is figure out what we're going to swap. Well, we need to know, to swap XI and XJ, this becomes something like, temp is XI, XJ is temp, like I remember this code, blah, 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 right? But we need to know positions 1 and 2. So for me, position 1 will be a random choice of all of the interesting positions. And position 2 will be another random choice of all the interesting positions. Note that there are very small odds that we pick exactly the same thing. I don't care. That won't end up being an interesting test case for us. And then value 1 is what we see on lines 1, and value 2 is what we see on lines position 2. And now I'm just going to make a copy of lines, except I'm going to swap the line at position 1 to print out value 2, and swap position 2 to print out value 1. So I'm going to go through all of these. Oh, we need to make some output file handle. We're going to open, what do I call it? We'll take a J and convert it to a string. Oops, sysargv1. And we're going to open it for writing. Right? Because I'm printing out 80 of these, I need to give them all a different name. I need to give each one a different name, otherwise we won't be able to see it. So in here, if I is equal to position 1, well, so normally the line for me to print out is just lines I. But if line is equal to position 1, then what I actually want to print out is value 2. Otherwise, if I is equal to position 2, then what I really want to print out is value 1. And now in my file handle, I just write out the line, plus a new line. There's probably no semicolon in Python. And now we do handle.close. 80, that's a lot of debugging to look at. Let's do this like twice to see if it works. And just for debugging, we'll say swapping val1 at pos1 with val2 at pos2. We'll just see how those go. All right. So here we've picked one swap. Let's see if this works. All right. Name random is not defined. Do we need to import random? All right. So we're swapping integer at 232 with baz at 9 and swapping raz with raz. Well, this is not going to do much, but the first one looks very interesting. So let's check our current directory. And look, here they are, 0.clx and this 1.clx. So what I will do is unlex this one to produce a cool file, which is apparently supposed to be different than the original. Now, that's a little harder for me to see, but let's pull it up in diff. Right, and so, we can see what's going on. The one on the left, foo inherits from int, and the one on the right, foo inherits from baz. And then similarly down here, because it's a swap, we changed two things. Over here, C is of type baz, and over here, C is of type int. So we've made a slightly different cool program. All right. And indeed, no, it has a different type error than the original. By randomly poking the program, we've shown off a different type error. And note that in this approach, we didn't have to know the error we were going for in advance very much. We just treated the program as data and systematically transformed the data. And we got something interesting out of it. This is one of the reasons people study program analysis. All right. So rather than 2, let's do like 80 of these. All right. So this seems pretty exciting. We've got a bunch of big swaps. But more importantly, we've got like a billion of these CLX files. And now what I want to do is try to parse or type check all of them. We know they're all going to parse, but only some of them are going to type check. So for everything that's a CLX file, we're going to type check it. Oh, and we noticed that for a lot of them, there are a bunch of different type check errors. But for some of them, we actually succeeded at type checking. I could send those to the grading server, but just to sort of show you how to do this, why don't we see about removing all of the newly created ones that actually successfully type checked. Right? So if you haven't run into it before, there's there's a useful shell program called basename, where if you happen to know the extension of something, you can chop it off in the shell. Right? So basename of foobar baz, if you try to remove bar, nothing happens. But if you have foobar baz and you try to remove baz, then it chops off the extension. So what I can do is for every CL type file, I can remove not only it, but its corresponding CLX file, or indeed just everything related to it. All right. And I don't want everything with a CL type file. All of our stuff starts with 0 through 9. Well, let's see if this works. Hopefully I'm not deleting all the Python files in the directory. That would be bad. All right. Now we have all of our CLX files, but a few of them from before, like 54, right here 54 type checked before, did not make the cut. 53 goes to 55. All right, but in order to submit these, I need to turn them into cool files. So now for everything in CLX, we are going to undo it for I in. Now we have a bunch of these CL2 files, and we're going to use base name again to rename them. Is this the most efficient way ever? No. Does it totally work? Yes. Notice what we're doing here is token pasting. Fun stuff. For I every single time. All right. So now we should have a bunch of CL files. And just to double check, we will ask cool to type check them. And we'll see what it says. And we notice that each one of them seems to produce some sort of type error. So now what I can do is make up our automatically generated. We know that submitting Harry Scary alone does nothing. Cool files. And now let's try to submit them to our grading server. We'll reload this just in case NetBadge is mad at me. Here are the automagic ones. And we want to submit to PA4t. And let's try it out. And now we notice that there are a bunch of these looking pretty good. Parse error, syntax error. It turns out that some of them, when we swapped types and identifiers, didn't actually produce programs. You can't always swap types and identifiers, but sometimes you can. This doesn't really matter. We just delete. I could have done this too. We delete all of the test cases that don't parse. All right. But now this is much more interesting. Randomly, literally, one of the cool programs we created, 10, reveals one of the interpreter bugs. And another one, 51, reveals a different interpreter bug. And over here, all right, 10 was pretty good, 31, 35, 22. Oh, we're halfway there. Wow. And we wrote a program to make 80 of these for us. Now, it mentioned that a number of these don't parse. Let's just check that out. In star.cl, do cool parse I, done. All right, and we noticed that a few of these have parse errors. And we could do the same sort of thing. We could delete everything that doesn't have an AST if we wanted to keep the number that we were submitting to the server low. But this was the basic theory. You can treat programs as data in multiple ways. This is one of the insights we want you to get at sort of sideways for this class. The cool reference executable is a program that you have access to. You can do anything you want with it, including trying to decompile it or understand it. That might help you find error messages, and then you make about half of your important test cases manually by reading the error messages and trying to see what's going on, trying to make tests that would violate those or show those error messages. But you can also get about halfway there by treating cool programs like Harry Scary or Unsort or anything else you have lying around as data and intentionally injecting faults into them. We did this just one way, swapping integers and types with one program, harryscary.cool, and we revealed 8 of the hidden interpreter bugs. And the suggestion is that by combining these two approaches, you can get the whole way there. All right. Best of luck creating a series of trying test cases.